we've done this stuff. We've talked about the idea of descriptive statistics, where we've done mean, median, mode as a measure of central tendency. We've done variance and standard deviation, interquartile range, and range as measures of variation. We've set up the normal distribution, more specifically the standard normal distribution for our z-scores. And that way we can get a better sense of exactly where a score is along the entire distribution. And now we're moving on to the idea of inferential statistics. So the idea that we are actually going to start drawing samples from a population. That's what inferential statistics are. And the soft way to do this is to start thinking about if we were to collect our own data, and this is how I really want you to think about this. How representative is our class, all you weirdos and me, of the population at large? I think in some respects we're pretty good, right? We don't have any like 8-foot-tall basketball players in here. Nobody's like super short. I think we've got a nice height. Like, we're good there. Right? Nobody's wearing Shaq's shoes. So we could say that we're fairly representative of a sample or of a population. But what we're going to do today is start thinking about, all right, what if we draw a sample from a population? How are we going to understand that sample as part of the larger distribution? And so today what we're going to talk about is the idea of evaluating the sample from our mean to the mean of the population. So we got a new term. It's called sample mean. Guess what? It's the mean from a sample. That's what it is. John?
Are the new quizzes and stuff up on Google?
Not yet. Okay. Other class. I'll get to it today. All right. So sample mean. Here's what we're going to do. We need to understand that there is another. Oh man, I should light a candle, get some incense or something. There is another distribution that we can put on top of a normal distribution. And it's the distribution of sample means. It's also normal. It's kind of like if you took a bell curve, got really high, and then made that bell curve in 3D, where it became a bell. So that no matter how you turn the bell, it was always bell-shaped. See, this is why you kind of need to get high for it. But I can't actually assign that in this state. So, all right, so you just gotta like get a goofy smile on your face and like, I remember what it was kind of like to be goofy one time. Like, get a bell. And the bell's always a bell, man, when you turn the bell. That's like a sampling distribution of the means. All right. Let's think about this, because we can take from any population, we could take an infinite number of samples. Hell, I can take an infinite number of samples from this classroom. There's 20-something people in here. I'll draw a sample of 3. And I can just keep picking 3 people, right? That is a sample mean, right? 3 people from a population. And I can just keep doing that over and over and over and over and over again. Those sample means themselves that I collect and draw will be normally distributed, which is why the bell is 3-dimensional. Okay. And here's the other really weird part about this. This is where we're going to start having conversations about sample size. There is in math, let's see if it's the next slide. Well, where is it? We'll get there in a minute. Let's skip that. All right. So here we have in our population, can't turn it off with this button, a regular curve, right? This is the distribution of ages in the population. Regular old curve. Actual people. According to this, the population mean looks to me to be 30. Right? That's the Greek mean. That's not X bar, that's mu. That's the population mean. How do we know this? I don't care. We just do. And a standard deviation, the real one, of 7. We're going to draw a sample from, this will be our sample. We'll draw a sample from the population. How old are you, Rich? 18. You, John?
20.
William? 21. 18, 20, 21. Average is about, take one from you, 19, like 19.75. Where's that on the curve? Well, it's right here. Did our sample have a mean of 30? No. Right? 18, 20, 21. We're not going to get a mean of 30 if none of you guys are over 30. How likely is it that we would get a sample mean of 19 3/4 when the true population mean is 30? I skipped that part. I just wanted to do a sample. How likely is it? It's all bucket on the floor, folks. We draw a curve, we put our spots. How likely is it? Yeah. So, Doug, thank you, Doug. You're like, I'll do some math. Is there any math out there you know that can give us the likelihood as a probability expressed as area of a curve? Greg's smiling. Gregory's smiling. He's got it. You don't actually have to do it. Right? We have this framework already. It's called a z-score, where the area under the curve represents probability. There's a little bit of a wrinkle, though. See, this is where I sold you guys on the first half of the class. It's addition, subtraction, multiplication, division. That's all it is. That's still true. But the hard thing is remembering when you do certain things. Because we've got a wrinkle here, right? We've got a sample size of 3. These 3 guys. That actually matters. That has an influence. So our normal curve that we have, that we've been using, we've been assuming that our normal curve represents a lot of numbers, like the whole distribution. When we get a distribution that is really small, the curve gets a little wonky. That's actually a term, wonky. It doesn't quite stay bell-shaped uniformly. Now, fortunately, there's this thing in math that helps us with small sample sizes. It's known as the central limit theorem. It's the idea that if you have a sample that is sufficiently large, you're normalish enough for the curve to still work. And for us, in statistics, We say you're normalish around 30. So I've given you a cutoff. 30. But what happens if we have less than 30? It's wonky. We got to use something else. Do with it. Got to use something else. There it is. And, hell with it. Make sure I get the extras back. All right. We're going to have to start paying just a little bit more attention. We're going to have to pay a little bit more attention to our sample size. This is the t-distribution. There's a long story out there. All right. It involves Guinness beer, quality control, and a mathematician. Guinness, they have most manufacturers have a process of quality control. Samsung needed better quality control last year when I taught this class, because it was about this time last year when the Note 7s were all catching on fire, which is not a desirable property in a cell phone. Alarm clock, yes. Fire starter, no. Not desirable. And so last year around this time, like I said, the Note 7 came out. Perfect example of the idea of we need better quality control. And Samsung itself admitted it. We'll do a better job. The question for them was, and for Guinness was, how much of our product do we need to do the quality control on before we are comfortable to release it out into the field? Now, quality control on a Samsung Note is like what? How do you know if it works? It doesn't catch on fire, so you just sort of plug it in and make sure it doesn't catch on fire, right? What's quality control on a Guinness? How do you do quality control in something like Guinness? You drink it. Any problems there? That's not a problem. No. How much? So if your version of quality control is drinking your product, yeah, more you quality control, less you sell. So Guinness had a vested interest in the idea of saying, how can we deal with really small samples? Because we don't want to quality control all of our product away. Right? We want to just take a little bit out. And how much is that little bit? Didn't work with a normal distribution. So Guinness and a mathematician working for Guinness invented the t-distribution. Thank you. Right? And they published it under a pseudonym. It was, and it was a much common thing when you're not necessarily looking for, tenure. To publish things, you would do it under pseudonym, and it's known as Students T. And so this is the Students T distribution. And the idea behind the T distribution is that we can estimate, like a normal distribution, where we are on the curve in terms of area, If you look at the picture at the top, it's still a curve, still remarkably bell-shaped. And we can do that when we don't know what the true population variance is at all. So there's a couple of hints on when you're going to use this distribution. One, small sample size. That's a hint. Yeah, good job, John. Write this shit down. Small sample size. The other one is when you don't know sigma. Got no clue. Because how are we going to tell the variability in all of the Guinness? I'm going to waste all of the Guinness. Right? We don't want to do that. So we need a distribution where we don't know the variance of everything. Let's see if I got that. There we go. So when we look at t, let's look at the curve. On this picture, we have 4 lines. The solid line is our standard normal distribution. Mean of 0, standard deviation of 1. Gives us that nice shape. The dotted ones are our t distribution. We can still put the t distribution at 0. That's not a problem. In terms of the shape, it is symmetric. So that's good. We don't have to treat the positive side any differently than the negative side. Treat them both sides the same. What is an issue is when our sample size changes. So we started our example with a sample size of 3. We're going to drink 3 barrels of Guinness to make sure that this batch was okay. Versus drinking 25 barrels of Guinness to make sure this batch is okay. Versus drinking 10. So we get a little bit of like degradation. We get a little bit of change in the shape as our sample size gets smaller. What happens as our sample size gets smaller? Well, first of all, the height of the curve goes down. What does that mean if our curve gets shorter at the mean? We're getting flatter, yes. But what does that mean? Exactly. There's more variability. Right? There's more variability around the mean, or at least let's say away from the mean. And look where that extra little area goes. It goes in the tails. Our tails are getting what? Taller, right? Our tails are much higher in this area here. So that's where the extra volume is going. The extra probability, the extra area, the extra volume is right here. So this is going down. Picture it. You're pushing down on it. If I could get like a little jello curve, right? Push down on the jello, what happens? It squishes outward. That's what our t distribution is doing. Smaller our sample, the more we're pushing that down. It's just a function of variability. Right? It's just pushing this outwards. So let's look at the curve. Yeah, you can keep that. I probably got this on my computer someplace. That was stupid. That was really dumb. Okay. I changed something. And this makes total sense to me, but I have to convince you. What's different from this curve to the previous one that I gave you? What's the first thing we should look at when we're looking at the tiny little picture at the top? The shaded area. Okay. So we're now moving to a world where we're looking at shaded areas. With the normal distribution, the shaded area was less than our z-score. We're going to be using shaded areas in a little bit different sense now because of Chapter 6. And I introduced this idea of hypothesis testing. And we're interested in shaded areas where? In our tails of our distributions. Okay? So this t-table puts the area that we're interested in where it belongs in the tails. Okay? Now, this is symmetric, but it's giving us the area of how many tails being shaded. One tail. So if we're doing a hypothesis that requires 2 tails, is that this? No. But I don't want to give you another one because that'll just confuse you if I give you one with 2 tails. So let's say, stay with me for a minute, that we're doing a hypothesis test where we want that 95% confidence, or in other words, our critical value is 0.05. How much is going to be in each tail? You don't have to tell me the number. You can just tell me how to mathematically get at the number. Half of 5, right? I want 5% in the tails, but I got 2 tails. So in each tail, I want how much? Okay. Take your tables and put, like, I don't know, a star right here. I can't do it because it's in Adobe. It won't let me write on my screen. Put a star right there. That's our favorite column. That's our default column. Does anybody remember what the z-score was to have 5% in each of our tails? Because I've memorized it because I'm a social scientist. William? There it is, 1.96. Why? Middle column with a sample size that looks like infinity. Really just means greater than like 30 something. This table actually goes out to 38. Middle column's the most important column. Except for when you get a question that gives you 90% confidence. Right? And says we want a decision rule where you have 10% in the tails. What do you have to do then? You have to remember I have 2 tails. I want 10% in 2 tails, which means I have about that much in a tail, 0.05, because I've got 2 of them. Okay. So small little quirk. Again, got to remember we have to learn how to read our tables. This table I think is the best one. Puts it right there in the center for you. Right? Gives you a good picture. Gives you the option of doing 1 tail or 2 tail. Gives me the magic number of 1.96 at the bottom. So I can go, holy crap, I should have just used the Z table instead. All right? So that's what this is. This t-table is exactly like our z-scores, except we're now using the idea of finding the t-value that corresponds to the appropriate critical value. So instead of the field of the table, all the numbers in the middle, being that probability, that number for the shaded area, we're picking our shaded area. We're saying if we want 20% in the tails, 10% in the tails, 5% in the tails, 98% in the tails, or 99% in the tails. Ah, fuck that up. The other way. In the middle. All right. Shouldn't have said 98. 2%. 1% in the tails. All right. Same thing. Area, tails. We're just looking at something different. Same exact thing. This is in here. This is our value at t. This is the t value that we're interested in. Okay. No. This one. Doug.
What are the numbers on the left side? How many you have in your sample?
Yes.
Numbers.
It is. All right. This is our degrees of freedom. It's based off of our sample. Degrees of freedom, n minus 1. If you're calculating one statistic, you do n minus 1. Thanks for reminding me about that. All right. You'll notice you got to have at least 1 degree of freedom to calculate the statistic, which means how many do you at least have to have in your sample? 2. You got to have at least 2 observations in your sample. So here's a question. Do students perceive themselves to be invulnerable? Yeah. You know how I know this? Because you all forget that cars park in a parking lot. That shuttle lets out right across the street here. And what do you all do? Cut through all the cars to get to the building. So you're like walking in between parked cars, and then, oh, look, no parked cars. Oh, wait, there's Dr. Wood ready to plow me over because I have darted out behind an SUV and not stopped to look. Every morning, I'm going to start honking. I'm going to be that guy. I'm going to slam on my brakes, honk, and rev my engine real loud and scare somebody. But they wouldn't hear me because they have their headphones in. But I can see it from here. It's that crosswalk. The bus stops there, and you all filter through. All right. Seriously, if I'm not here someday, it's because I've accidentally run over a student. Because you all love to dart in front of me, and that is not a threat. All right. That is me being a cranky old man. All right. Do students perceive themselves as being vulnerable? Well, the ones that get off the bus stop do. It's known in the U.S. that people typically die at age 75. A sample of 17 students were asked to predict when they themselves would die. Listen, it comes from the book. This is not me. Okay? What's our N? What's our sample size? All right. What's our degrees of freedom? Their scores averaged 84. Guys think you're really going to live forever. It's an extra decade. I mean, have you seen 84-year-old people? It's not the best 10 years of your life. All right? With a standard deviation, is that a sigma or an S? So that is the standard deviation of my sample and not the, and this is why we're using a t-table. We use the t-table when we don't have the population standard deviation. We're also going to use the t-table. Why? Yeah, because it's a small sample. Right? Central limit theorem says normal above 30. Are we above 30? No. That's why we're going to use the t-table instead of the normal distribution. Here's a different example. Students are taught, a reading skills program are tested to see how many words they can correctly read per minute. When you have kids, elementary schools are obsessed over words read per minute. My daughter can speed read. She reads 220 words per minute out loud. And she talks really fast like this, and she goes through and reads. She can say it. I don't know why they're obsessed with this. All right. A sample of 20 children in the program have a mean of 150.35. That's like first grade level. Abby's in second grade. She's in the 220s. It is estimated that in the population, children read with 124.81 words per minute and a sigma of 43.26. Does the reading program improve reading ability? This, we use our z-scores. Why? We're talking about a population. We have sigma. We are going to maybe use that 20. Hold on a minute. All right. Yep. Yes. In elementary school it is.
So if you have sigma, you don't use this chart?
If you have sigma, you don't use
This.
right. We have the population information. Yep. So we have a mean of 124.81. The students in the program are reading at 150.35. We need to start using our hypothesis testing framework. Right? I've given you the math. We got through the midterm, you all have the math. Now it's time for the social science part of it. So we're going to start thinking in terms of null and alternative hypotheses. Our null hypothesis is that the reading program has what effect? No effect. Right? Null hypothesis, no effect of whatever your independent variable is. Alternative hypothesis, the reading program does what to children's reading words per minute? We hope it helps. We really hope our reading program doesn't make them worse. That's probably what would happen if I did a reading program. Like, hey kids, let's do 5-syllable words, because you need to know big words. So my daughter, Abigail, can read 220 words per minute, but I had to explain to her what pale meant. Like when you look pale, you do not have a bucket on your head. Because she didn't know what that word is. But she can read it really fast. She just had no idea what she's saying. All right. So we're hopeful that the reading program gives us a above average estimate. Right? We want the kiddos to be better. So that's our alternative hypothesis. So again, we're going to start thinking about our curves. When is our sample mean so different from the population mean that we are comfortable rejecting that null hypothesis that we assume, Matt, is true? This is where the decision rule comes in. 5%. Okay? We're going to take our 5%, split it up into two tails, because quite frankly, the reading program could be bad. It could. It could make them worse. Could make them better. So we're going to say, listen, this difference has to be greater than 1.96. for us to reject the null hypothesis. So we got what, like 124, and we got to know where our 150 something is, right? We want to know if it's far enough away that we can reject the null hypothesis. Does that make sense to everybody? Because if you can understand this, then the rest of the class is going to be easy. Is our sample mean different enough from our population mean? Got our rejection rules, magical 1.96. And again, it's not the math that's hard, it's understanding why the process is different that's hard. So I got to throw a wrinkle in there. We're going to change our sigma if we're using a z-table. We're going to change that. It's now a sigma of our sample means. Because remember, we're treating this normal distribution as a distribution of means. Remember, we got really high and the bell became symmetrical and three-dimensional. So we got just a little wrinkle there. Because we have to incorporate the size of our sample. So here's what we do. It's not hard. Two little tricks. We take our population, variance, standard deviation, divide it by the square root of our sample size. Somebody in their head's going, why? And all I want you to know is, because. Not because I said so, just because. Sorry. That's all you get today. Because. There's a reason. It has to do with the curves actually not being what I told you they are, but it's fine. This is not hard math. Again, we've got the magic button. Turn your phone sideways, hit the square root button, and it's of n. It's of the sample size. So in this example, the n was 20, and the square root of that, divide what we were told the standard error of the mean was, standard error was, you get a new number. It's a good thing. I got 4 more minutes. Nobody's going anywhere. The great part is the top is still the same. So we got our sample mean. This is our kiddos that did the reading program. This is how far they are away. I get a z-score of 2.64. Is that good? Is that good? Why is that good? What's it mean? So where are we? We're towards the tail? Whereabouts in the tail are we? Well, you could look it up in your table if you had a z-table in front of you. But I don't need to do that. I'm happy. I'm glad my daughter's in that reading program. Why? Because it's the what? It's the 99th percentile. I'm way out in those tails, and what region of the tails am I in? Shaded region. So I can do what to the null hypothesis? Doug, what can I do to the null hypothesis? Yeah, you're right. Just say it louder. I can reject the null hypothesis that the reading has no impact on students. Why? Because they're reading 25 words per minute more. They're 20% faster. I'm way out here in the tails. Right? Not just the 95% area. I'm out here past the 99% area. This reading program's good. Reject the null hypothesis and accept, or at least do not reject the alternative hypothesis, and say that the reading program, actually, there's evidence that the reading program benefits kids. Yeah, I'm going to finish it up in the other video. I'll do the T version in the other video. It's exactly the same. And then I'll go through a bunch of examples so you can see my decision making when I'm trying to test these hypotheses. It'll be good. You'll learn a lot. Watch